Now we're going to look at a trajectory where you have acceleration in one dimension. And of course we're going to use gravity. Usually you do this just by throwing chalk, but here we're in Texas, so we're going to do it with a gun. So we're going to have this Nerf gun shoot its bullet and see if we can watch the trajectory. All right, we're loaded and mounted. Let's see if we can see a nice trajectory here. Yeah, that looked okay. It kind of came down like I wanted, but I don't know, the curvature, it's so fast this way and it falls so slow that way. I don't feel like you could see it. I guess I could increase gravity or compress space. Which should we do? Let's go with the latter. Let's see, so here we go. There's a lot of work, hold on. Okay, that's gonna hold. Okay, just give me a minute. Ooh, I look good. Early, I look young. All right, so let's come over here and try this again. Let me cock the gun. And now you might be able to see the curvature we're looking for a little bit better. Let's see. And yeah, no, I think it looked better that time. I feel like maybe you could really see how it's supposed to go down. Oh, I forgot. Let me. Oh, whew. Okay. Let me get this out of the way. And now let's analyze this kind of motion. Here we go. So what we had was an object here, x, y. So we're plotting the trajectory, not the kinematics plot. And it started out flat and it just kind of went down like that. Right? So to analyze this, let's draw some r vectors. Actually, let's draw some delta r vectors, some displacements. We know we started like this, and then there, and then there, and then there. So we already talked about how you look at the difference between two proper r vectors from the origin, and they give you delta r. So there's one delta r, and here is the next delta r, if these are uniform in time, and then there is the next delta r. So what you see here, we could label them 1, 2, 3 for 3 uniform changes in time. And what you see is that delta r1 does not equal delta r2. It's because the path is curving. So we can think about what did that mean in terms of physics. Well, that means that delta v1, well, we ever call it an average, the average velocity on this one does not equal the average velocity on this one for 2. I'm sorry, I don't need the deltas in there. Just the average velocities in those regions are different. Delta v, or v average 1 and v average 2. So if the velocity is changing in time, that means the a does not equal 0. That has acceleration. Right? And of course it does. Gravity, right? It was accelerating down. Makes perfect sense. So it was moving gravitationally or it was following this way, moving uniformly that way. So let's see if we can do the constant acceleration kinetics. But in terms of the position vector r. Okay, so let's write r. And we could start out, if you want to be real general, let's be real general. Let's start out and just say it's always x initial plus v x initial t plus 1/2 a x t squared I hat plus be y initial plus v y initial t plus 1/2 a y t squared j hat. Because this is constant acceleration kinetics for each case. So now we just have to go to our problem and plug in the right values. Some of these are 0. So in this case, in x, let's see, we don't have an initial x position, right? We start out at x equals 0, and we have no acceleration in the x, because gravity is just in the y. So x really is just that initial vxi velocity, right? We shot the bullet with an initial velocity, vxi. So that's the only thing that goes on the x, I hat, plus y direction, we did have an initial yi. Right? So yi would go here. We had no initial velocity in the y. We shot it straight. All the initial velocity was in the x, so nothing in the y. So that term is 0. And the acceleration in the y was negative. It was negative 9.8 meters per second squared. This time I'm not defining down as positive, I'm defining up as positive, since I wrote that up with a y on it, right? So we have to actually plug in the negative value here. So I'm going to put minus 1/2 9.8. We'll assume we're in MKS, I won't write the unit, and t squared, j hat. Okay. And then that tells you everything you need to know about the position. You have the position at all time if you know the initial velocity in the x and you know the initial position in the y. And you can further use this. So you want to know the velocity at all time, the velocity vector. That would be vx I hat. I took that derivative. All that's left is the initial velocity plus the derivative of that is 0. And then this is minus 1/2 gt squared. So let's see, it'd be take the derivative, 2 cancels that, 2 minus 9.8 t j hat. So the velocity is just the constant x velocity and the y velocity going down. Let's do the acceleration. Why not? So the acceleration is just another derivative. Derivative in the x is 0. No acceleration in the x. That makes sense. Derivative of that is minus 9.8. Minus 9.8 j hat. Sure enough, it recovers what you would expect. Okay? Is that we have acceleration down. How do you use this? What is the point of this? One way you could use it is, say you were asked what is the angle of the trajectory at a certain time. The angle of the trajectory has to do with the velocity vector. Right? So you need the angle of the velocity vector at a certain time. Well, you plug in that time, and then you have velocity as a vector, x component, y component. And if you want the angle, inverse tangent of y over x. Right? So we'll show you some problems where you can use these things, but the key is if you can just write that position vector, everything usually comes out of that. We've had a lot of very vectorish treatment of 2D kinematics. Now let's do something real. Let's do the shoot and drop. This is a very well-known famous demo where you have two objects released at the same time. One goes straight down and one gets shot forward. And the age-old question is, which hits the ground or the table first? Maybe the one that drops it first. Maybe the one that got shot is moving a little faster. Let's apply some physics to it. So we have a shoot and drop set up here. So it's a little spring-loaded mechanism, and one mass is hanging on a rod, and it's just going to get the rod pulled out from under it, and it's going to drop. The other mass is going to be pushed by that same rod, and it's going to shoot out that way. So they'll go at the same time when I release the spring. So we can just do a quickie drawing here. So one, this will be shoot, right? So it's going to get an initial velocity like that, and one is going to be drop, and it's just going to drop like this. It's just going to drop straight down. All right, so before we get to do it, we have to do the equations. So the way I would approach any kinematics problem is write the position vector for each mass. I know you can do it without that, but it's usually good to kind of do that, right? So RD, the position of R drop is, let's see, in the horizontal, if we pretend it's at the origin, it has no motion in the horizontal. We have to put the origin, basically we can imagine they're both at the origin on top of each other. So the position of this one in the horizontal, 0, not going to move. In the vertical, the y-axis, it has an initial height, y naught, and y naught, or y initial. I won't be old-fashioned, y initial. So y initial, and then it's going to drop. It has no initial velocity, but it has an acceleration down, right? So I'll put minus 1/2 gt squared, j hat, where g is 9.8 meters per second squared. And then shoot. Let's look at R shoot. That's going to, let's see, in the horizontal, in the x direction, it has no initial position, but it does have a velocity. So we would just say it is v initial times t. It has no acceleration. So there's its I hat, and its horizontal j hat. We'll also pretend they started both at the origin, and it's just going to come down. Starting out at the same height, y naught, or y initial, minus gt squared j hat. Even if you don't need those, it's good to write them down. There will be more complicated problems where you need them. Let's see. So the question is, which hits the ground first? When do they hit? So the y component tells you when they hit. I like to imagine you're talking to the equations. You ask the equations, when does it hit the ground? And it tells you when this is 0. Right? And when does this one hit the ground? When this is 0, because that's the y position. So we actually don't need the x position to answer this question. So for drop then, you'd say when this equals 0, yi, let's see, when you have the initial minus 1/2 gt squared equals 0. And now it's a special time, so I'm going to put a little hit down here. I usually do a star, but there's a 2 in the way, so I'll just put hit. And here, when does this one hit the ground? When yi minus, oh my God, did I leave a 1/2 off there? Minus 1/2 gt hit squared equals 0. This is a specific time now, so that's why I put a hit on it. It's when it's equal to 0. And you could solve those, and you'd see, when does this one hit the ground? T hit. For that one, oh, well, it's just this goes over here, and it's 2yi, or square root of 2yi over g. And you'd solve this one, and of course, it's the same thing. The answer to the age-old question is that they hit at the same time. Because in the y, they're basically doing the same thing. They're both falling. So horizontal motion and y motion are not coupled when you're near the surface of the Earth. The horizontal has no gravitational force, no accelerations, and the y does. Therefore, they remain separate when you're just freely moving. So let's try it out and see what happens. So here we go. I'm going to flip the switch, and this is the one that is going to be shoot. It's going to go that way. This is the one that's going to be drop. It's going to fall straight down. And usually the best way to tell if they hit at the same time is with your ear. So let's listen for it here. I only heard one collision. I think they hit at the same time. So one quick thing we could do, since this is supposed to be a real world problem here, let's do some calculations. yi is about 0.78 seconds. So what is this t hit? That's the square root of 2 times 0.78 meters over 9.8. It should be about 0.4 seconds. So you can go back and watch the video and decide if it really took 0.4 seconds. Whenever I do the shoot and drop demo, I do everything I can to convince you that the two masses hit at the same time. And we do all the physics to show you that the two masses hit at the same time. And I even will let students come play with it and see that the two masses hit at the same time. But no matter what I do, at least one person after class says, now, if shoot were going really fast, it would have hit later, right? I'm just like, oh. Inside I just scream, no, that's why I'm doing this, just explain it. But on the outside I go, no. If it's going really fast, it'll still hit at the same time. And they say, what if it was an arrow? And I say, if it's an arrow, it'll still hit at the same time. What if it was a bullet? Still hit at the same time. They will always hit at the same time. We did the demo, we did the physics. But technically, the student is right. Eventually, they won't hit at the same time, and it's actually enlightening because it happens when your model breaks down. We're always making models when we do physics. So here, what is our model? We have this region of space, we have this thing that we drop, we have this thing that we shoot, and we say gravity is always straight down. And in that case, yeah, they'll always hit at the same time. But what if you shoot it really hard? Oh yes, they'll still hit at the same time. What if you shoot it really hard? Well, eventually the Earth is going to curve away, right? We modeled it as a flat Earth. It's not a flat Earth. Eventually, yeah, they won't hit at the same time. Eventually, you'll put this one into orbit. What else might throw it off? How about air resistance? This one, eventually, if you're shooting really hard, feels a lot more force due to air resistance than the one dropping. So that might slow it down in a sort of a weird way where X and Y are coupled. So it's fairly complicated to think about. What about the fact that we're on a rotating Earth? There are extra forces that show up because we are not on a still Earth. We're actually spinning around. So yes, eventually, if you shoot it hard enough, they won't land at the same time. But in terms of what I just showed you, things that will happen in here and on your exam, they will land at the same time. A couple more questions we can answer about shoot and drop. How much further did the shoot go than the drop? And at what angle did shoot hit the table? So let's see, this is sort of one of those two-body problems, although this one's easier because one of them didn't move in x, right? So how much further along the x-axis, right? So the dropped mass is just 0, right? So the position vector is pretty simple for that one. It did not move in x. And shoot, if we think back to the x component of that position vector, basically it had 0 initial position and it just moved with constant velocity. So it would be at v, I think we called it v initial, the initial horizontal velocity times t hit, right? Because this is how far it got before it hit the table. Right? This is how much further shoot was than drop at the time that they hit the table. So we could then say the difference of those two, of course, is just this value because that one is 0. And you could plug in things that you know, v initial times the square root of 2 y initial over g. But you can't solve for it because we don't know how fast it was going. All right, so what are we going to do? Well, that's why the ruler's here. I know I saw it hit at 1.3 meters. All right, so instead of calculating how much further it went, we just measured how much further it went. For fun, let's calculate the initial velocity. So let's see, if this is 1.3 meters vi, and this was 0.4 seconds. We did that last time. So 0.4 seconds. So in the end, you get that the initial velocity was vi was 3.25 meters per second. Okay. Not exactly what it asked, right? It asked about this number, 1.3. But we were able to calculate for fun 3.25. So that was a fairly straightforward application of kinematics. Here's a weird one. At what angle? So that is a little unusual. Let's draw shoot's trajectory here for a second and see if we can figure out what they mean. So it's a little cube and it shot like that and it kind of hit the ground like that. And the question is, at what angle, theta, does it hit the ground? So to get that, you got to think about what's really defining this trajectory. It's really, as you go from point to point, it's those little delta r vectors, right? As you go from here to here, that's a delta r. At the beginning, delta r was flat. It was moving that way. But the quantity that gets you that delta r is actually v. Remember that velocity is delta r over delta t, right? Average velocity. Or instantaneous is the same thing, just with a really small delta r. So it's really the velocity that tells you the direction of the trajectory. So if you needed an angle for the trajectory, you got to look to the velocity. Now how you get it is you break the velocity into components at this time, right? So really the velocity at this time is along the trajectory, and it's down like that. It's the velocity of shoot, and it has a component down like that, and it has a component horizontal like that. And the theta you want is here, so you do your opposite side angle, whatever it is from junior high, I don't remember. Basically this theta equals that theta. That's what you care about. So there's your theta, and then you apply tangent, right? Tangent is opposite over hypotenuse. So you find out, you remember that tangent, in this case, the way I set it up, is Vy over Vx. It's just the tangent of theta is the ratio of the two velocity components. Depending on where this angle you're looking for is, you might be shooting it weird. You might sometimes get Vx over Vy. Usually, though, it'll come out Vy over Vx. So let's see then if we could actually get that angle. Let's see. So the angle, just as a summary, is of the trajectory from delta r, which is the same direction as v. Okay, So we're getting it from V. All right, so let's see. So tangent theta. And let's see, what numbers do we have here? Vy over Vx. Vx we just figured out because we had the initial horizontal velocity and it doesn't change. There's no acceleration in the x. So we put 3.25 in the bottom, right? But now we need Vy. Oh, let's see, it accelerated over a distance. So we got to go back to that equation. V final squared equals V initial squared, which was 0, plus 2AD, plus 2 times A, 9.8 times D, 0.78 meters. That's how high it was. Remember? Let's see, so you worked all that out, and you multiply that, take the square root, and you get 3.9 meters per second. So Vy, when it hits, is 3.9 meters per second. So 3.9 here. You get something a little bit bigger than 1. Inverse tangent of whatever that is, a little bit bigger than 1, and you get theta is 50 degrees. As you'd expect, it landed when the two components were about the same, so it's near 45 degrees, right? It's 50 degrees. So if you watch the video, maybe you can tell it really was at 50. So this is how you can use kinematics to get much more than just where something ended up.